Now here's the next topic, subgroups, which is 9.4. It follows some axioms. So let's move towards the definition. As you can see on your screen, the definition of a subgroup is if a subset H of an abelian group G is called a subgroup of G, it's denoted by like this, if its closure under addition, if its closure under identity, and closure under inverse. Properties ensure that H is itself an abelian group under addition. We don't need to stipulate associativity because if addition is associative for all elements of G, it will certainly apply within H. Now here move towards the next definition, which is a coset containing G. If I have supposed that G is an abelian group, H is it's how we denote the subgroup. If G is belongs to the G, we define the coset containing G to be like this: G plus H such that H belongs to the H, which is another group. And we denote it by G plus H. The elements G is called representative of the coset. So it on your screen, which says that if G is equals mod of Z12, mod of integer 12, and H is the coset which is given as you can see on your screen, then H is lesser than or equals G. It's obvious. The cosets of H are these: 0 plus H, 0 plus H, 1 plus H, as we'll adding 1 in this set, and 2 plus H, here we'll adding 2 in this set. There are all other there are some other representatives, but they lead to the same cosets. For example, if I add 5 in it, I'll get 5, 8, 11, 12. Remembering that 5 plus 9 equals 2. How? Because we are concerning with mod of 12, and this is same as twice of H. So as we move towards further, we'll get the same elements. Here's the theorem number 1 on your screen. If G is an abelian group and H is lesser than or equal G, then distinct cosets of H are disjoint. As I have written the statement for your sake of simplicity, this means that if two cosets have one element in common, they must be the same coset. Suppose G belongs to A plus H and the another one G belongs to B plus H, and we can write it as G equals A plus H1 equals B plus H2 for some H1 where H1 and H2 belongs to our H, which is another group. Hence, we can write it as like this: B equals A plus H1 minus H2. So for any H belongs to H, we'll add both the sides H, small h, like this H, right? Like this, as you can see. Here's the equation. So this is also belongs to the H of the group. This shows that B plus H is a subset of A plus H. This is a newly generated A plus H, and it's a subset of B plus H, right? So similarly, A plus H is a subset of B plus H. So these two cosets are equal, right? So let's move toward the next theorem. Here you can see the theorem number 2, which is Lagrange's theorem on your screen. What it says: if G is a finite abelian group and H is lesser than or equals G, then H divides G. Here is the proof. Suppose that there are m distinct cosets. As we studied, the coset is something group we have something group given to us, and we are adding some numbers to it, and but we are getting related material which is given as another group, which is given to us in another group, which is G. If G is a finite abelian group and H is less than or equals G, then H divides G. This is a statement, and here's the proof of the theorem. Suppose there are m distinct sets of H, since every element of G belongs to exactly one coset, and since they are also have the same size as H, as we have studied in the previous example, we have H equals m times of H, right? So now here's the next theorem 3. on your screen, which is also a Lagrange theorem. What it says: if G is a finite abelian group, then every element of G has finite order. Moreover, the order of G must divide G. It's so obvious, but we have to prove it. How? Let G belongs to the G. It's some element we are taking from G, and suppose that G is finite. Since like this must be a finite, we have mg equals ng for some integers where mn are integers with m is greater than n. So we can subtract it. So it follows the next part as we have studied in theorem number 2.